Hello everybody, Professor Johnston here, and just wanted to go over the material we covered today, which is looking at Brownian motion as a limit of a binomial model. And this is, of course, for MTH 346, continuous time finance. And so what we're going to look at is we're going to look at a binomial model first. And a particular binomial model, we're going to choose our time step, delta, to be a small change in time. So we're basically going to look at this process that changes every delta units of time. So if you think of maybe the whole time period being a year, maybe delta would be like 1 day, for example. And every delta units of time, so every day, for example, the process either goes up or down by some amount sigma square root of delta. Okay, so we're going to choose these steps for a good reason, as you'll see. And the process goes up at delta, 2 delta, 3 delta, so on and so forth with probability p, and it goes down with 1 minus p. So your typical binomial tree would be here, right? Let's say you start off at 0. You could either go up or down with probability p, 1 minus p, go down. And then that would be a time delta, and then at time 2 delta, these would be like slices of the tree. Time 2 delta, you either go down again or up, or vice versa, down and up. It's up or down. So you can see this tree would grow over time, and on the right here is a sample path, just an example of what might happen. So time 0, you're here. Time delta, say the end of the day, closing prices of a stock, for example, you may have gone up by sigma times square root of delta. And after the second day, you go down by sigma square root of delta, so you're back where you started, x equals 0. And then 3 delta, maybe go down, 4 delta, you go down, and so forth. So every step, so you take a step every delta time, and every step is either plus or minus sigma times square root of delta. And what we're going to show is that if we let p, right, so p would be the probability of going up here. If we let p be equal to this special value, 1/2 times 1 plus mu sigma square root of 2, then we'll find out that as delta goes to 0, this process sort of becomes the Brownian motion, meaning it satisfies all the requirements for being Brownian motion, right? Independent increments, normal increments, the mean is going to be mu times change in time, variance is sigma squared times change in time, right? So we're going to prove that. And then after that, the next lecture, or the next set of slides, we want to show how this links into our binomial model, no arbitrage binomial model for stock prices, where these probabilities are sort of the risk-neutral probabilities that we all love so much. So we're letting this, time delta be chosen. We're letting the up and down moves be specifically equal to these values, and then we're letting the probability of going in an up move be equal to this. And we're going to show it's Brownian motion. So just to rewrite this process, x of t, we can write it as a sum of Bernoullis. So at every time delta, so this would be x of 1 would be at time delta, x of 2 would be at 2 delta, 3 delta, and so forth. This random variable, xi, is either plus or minus 1, So we can write our process, x of t, we can write it as our initial value plus the sum of all those Bernoullis times sigma. Now there should be a square root of delta in here, I forgot that. So it should be sigma squared of delta times the sum of all those Bernoullis, right? So in other words, if all of these were positive 1, if all just so happened you had step-ups every time instant delta 2 delta all the way up to n delta, then it would be looking at x of 0 plus n times sigma squared of delta. So we're just rewriting this process as the sum of Bernoullis, right? Sum of Bernoullis. And you can look at this example here. And the reason we do that is because we want to be able to look at the expected value of this process, x of t, minus the initial value x of 0. So what we have in shorthand notation here, I've got the square root of delta back again. If we can write that x of t, let's say n delta, is equal to the initial value plus sigma square root of delta times the sum of all those Bernoulli random variables. Now there are n of those, which we can also write as t divided by delta, as long as we remember we have to take the integer floor, like, as long as we remember that. So now, if you remember, for a Bernoulli random variable xi, the expected value can be written as this here, which if we plug in our special value for p, right, we get mu divided by sigma times the square root of delta. And then if we take the expected value of xi squared, which is 1, that allows us to calculate the variance for each one of these Bernoullis. And remember, they're independent, right? So it's an independent flip of a coin every delta time. And so the variance can be written as this guy right here. So we have the mean and we have the variance for each one of these Bernoulli random variables. So step 2 is let's figure out what the mean value for the differential is, x of t minus x of 0. Well, I'm just going to plug in the formula for that differential. And because of the linearity of the expectation operator, that allows us to bring the expected value inside, and we can replace that with the expected value for each Bernoulli. Now, there are going to be n of those, or t over delta of those. So when we calculate that, we have sigma squared root of delta, that's from here. We have the mean of each Bernoulli, right? That's what we did here. That's there. And then we have n of those, or t over delta of those. And when you start crossing things out, you're left with just mu times t. Very interesting, right? Very interesting. In fact, that's what we want. So we designed it that way. And then the variance, similarly, the variance can be sort of brought inside, not because it's linear, but because the xi's are independent. And remember, this sigma square root of delta becomes sigma squared delta. And the variance can come in, which is a constant again. And so we have n of those, or t over delta, of those Bernoulli variances, right? Bernoulli variances here. And then sigma squared delta. And that gives us sigma squared t times this term here. Okay, so we have the mean of the differential and the variance. And then letting delta go to 0, we see that the mean differential remains the same, right? There's no delta here. And the variance as delta goes to 0 is equal to sigma squared t. That's exactly what we want. Because remember, if this is going to be Brownian motion, right, defined by that equation, mu dt plus sigma dz, then the differential will have to have mean mu t, and the variance of the differential will have to be sigma squared t. So that's how we designed it. So we let delta go to 0, n gets really large, and we're adding a bunch of IID random variables together. So what can we do? Hey, as long as we have finite variance, central limit theorem. That's the beauty of the CLT, right? And so when we add all these things together, it tells us that this differential, as delta goes to 0, doesn't have to go to 0. I mean, well, it's pretty close to normal, even when delta is just, fairly small. Becomes a normal distribution. It has this mean and has that variance, right? So that's looking very familiar, right? Hopefully that's looking familiar. That's what Brownian motion should be, right? That's what Brownian motion should be. And then, so in the limit, we can show that in general, right, the differential, any differential can be written as this, a normal distribution. And non-overlapping intervals are independent because if they're non-overlapping intervals, there'll be non-overlapping sums of Bernoulli random variables, so therefore they will be independent. And then, of course, assuming x of 0 is equal to 0, assuming with probability 1, and then you can show it's also because of this, it's stationary, right? They're going to be stationary distribution, stationary increments. So it follows that x of t follows Brownian motion, meaning that we have this sort of fictional stochastic differential equation. The reason I say it's fictional because it's really just a formal way of actually saying this, right? Which this here we can actually define mathematically, right? This is equality in a mean square sense, and this is the Ito integral, which is it's very much like a Riemann integral, but we have random increments. Expected value of this goes to 0 here. You're just left with mu times t, and this simple integral, basic integral. And then the variance would be sigma squared times t. So that's it. So that tells us, how we go from Brownian motion, continuous model, is the limit of a discrete model. And this will come in handy because, continuous model is great for doing some stochastic calculus, and we get some analytical results. In particular, we get the Black-Scholes formula, which gives us a literal formula for calculating the price of a option in terms of a number of important variables, most notably sigma. But if we want to implement this Brownian motion model and compute, say, more complicated options that we don't have an analytical solution for, then we have resort to the binomial model, since we know that they're linked together in this limiting sense, right? All right, so stay tuned for the next movie.